think.
Yes. Can you hear me well?
Yes.
Okay, now I'm trying to share my screen. I hope you can see my screen.
Yes. Yes, we can see the experiment set up. Yes, please go ahead. Yeah.
Yeah, okay. So, hello everybody. Today I'm going to introduce to you AttriInfer, which is a paper that discusses inferring user attributes in online social networks using Markov random fields. This paper was published in 2017, so it's not very recent, but it's also not so old. So my plan is first to give some motivation on why this should be interesting, and then I will introduce some basic definitions that will help us understand the problem in a more formal way. Then I will give an overview about the proposed model and what's new in this model. Then I will give an idea about pairwise Markov random fields, and this will help me to give more details about the model. And finally, I will show how this model performs against its peers. So many parties can be interested in users' private information for many reasons. For example, advertisers should be interested because this helps them to apply target advertisement efficiently. So if they know that you are single or married, male or female, or so on, they can push a relevant ad for you. Cyber criminals also because this helps them to like perform social engineering attacks, and they can abuse you or sell your data to whomever interested. Data brokers are companies that are actually specialized in collecting data, so they just collect the public data that's available on the World Wide Web, and they structure them to be sold to other parties that might be interested in these data. And what makes a data broker special about the other is one thing would be like that they also provide information that's not easily available on the World Wide Web, and this can include private information being inferred. And of course, service providers themselves, because this helps them to customize their service, and hence people will like stay longer times on these platforms, which in return means more money for them. And this list is actually very long, so it doesn't only include these parties, because it depends on the context. So maybe some people who train machine learning models for problems that don't have enough data will be interested in inferring some private information and building their model upon that. Authorities in some countries might be interested too. So it's a very long list, and in return, we should conclude that this is a very important problem. So the author of this paper classifies attributes into three categories. First, binary attributes that can have only two values, like gender, male or female. Multi-value attributes are attributes that can have more than two values, like single, married, divorce, like the marital status can be single, married, or divorced, but a user can only has one value out of these. So a user can either be single or married or divorced, but not single and married at the same time. And the third classification, he states, is the multi-value, multi-label attributes, which are the attributes that can have multi-value, and the user can actually have many of these values. So cities lived, for example, I've lived in Cairo, now I live in Saarbrücken. You can work for many companies and so on. So he approached the attribute types in this form because he states that the last two types can be encoded into the first type, and for him this is an important feature that he will use later when introducing his model. Now moving to part two, which I was saying that I want to introduce some terms. So these actually are the terms. Some of them are quite intuitive and others might need some more formal definition. So a target user is the user that we are trying to infer an attribute for and to know more information about. And a positive training user and a negative training user, meaning is that a positive training user is somebody who has this attribute. So for example, if I'm trying that to infer for a target user that somebody has worked for, if he worked for a company or not. So a positive training user would be a user who worked for this company, and a negative training user would be a user who didn't work for this company. And here the definition of the negative training user also needs more formalization, because some people do not provide information about the place where they work. A negative training user would be with respect to the author, would be a user who provided similar information but didn't provide this specific attribute. So for example, if somebody provided information that he worked for like 5 companies, which does not include the company that we are interested in inferring in the target user. So this means this has high probability that this person does not have a reason to hide this fifth or sixth company. So we will consider him a negative training user if he provided similar information, like provided some companies but not this company. But if he didn't provide any companies at all, we cannot consider him negative training user or positive training user because we don't really know. An edge is just a connection between two users. You can think of that like a friendship between two people on Facebook, or people following each other on YouTube or Twitter. A private attribute is the thing that we are trying actually to predict, and a public attribute is that is the information provided by some user that he worked somewhere or lived somewhere or so on. Behaviors are like likes, comments, interactions, ratings or reviews for some application or music on some platform. Neighbors are people who are connected to some user, and actually this definition also can be extended. Like you might say, okay, I will consider neighbors are only the friends of some person, or you can consider friends of friends, or you can consider friends of friends of friends, or so on. And you can, like, the width of this circle depends on the computational power that you have, and also the effect of increasing this width on the model complexity. So the definition is not very well defined, and it depends on the context. Homophily is a very, very important definition, and it basically states that people who are neighbors or who are connected are more likely to have the same value for a certain attribute. So for example, if me and you are friends on Facebook, this makes high probability that we'll live in the same city other than living in different cities. And this concept is very important in our model and how our model works, and we will try to mathematically formalize it in order to make use of this fact. The last three definitions, node potential, edge potential, and messages, are actually relevant to the actual model being used, which is the Markov random field. So they cannot be understood very well here, but you can imagine them as, for example, if we have a Bayes network, then a node potential would be the probability distribution of a certain random variable, and the edge potential would be the conditional probability of a given random of a random variable given the other. And the message sent from a node to another is basically like if we are trying to predict some value for such node, or the probability distribution for a node, it might depend on other node. So the other node needs to send its probability distribution to this node in order to compute some distribution at the target node. So for example, if x is dependent on y and w, then y and w need to send their probability distribution to x in order that we can compute the probability of x. We will get more into these definitions when we see the Markov random field, but this is just roughly enough for now. So the previous work in this problem, there is a paper which was introduced by Weinsberg that uses only the behaviors of user to predict a private attribute. So this means that we only predict the private attribute using likes, interactions, reviews, and so on. And there is that very important work, which is Vial, because Vial combines the behavior as well as the social graph, meaning that I will infer the attribute using likes and such things, but also using the friends or the connected users to our target user. So our model uses the same idea like Vial. It uses both the behaviors and the social graph, but what's new in our model is that it considers both positive and negative users, with the definition of the negative user that I stated before, that he has similar public attribute, but without the same value that we are trying to predict. Yes, and what's new also about our model, beside this point, is that it scales. It's faster than Vial, and this is because Vial uses random walk to estimate the target attribute for a given user once at a time, but our model can do that for multiple users simultaneously, as we will see. So the first part of our model is easy to understand. It's a logistic regressor. So we try to compute the prior probability, and by prior we mean that it's a probability that's calculated without being given the surrounding users, only using the behaviors. So for that we just use a conventional logistic regression with this equation. So the prior probability that the user U has the attribute x equal to 1 is equal to 1 plus 1 over 1 plus the exponential. This is the logistic regression equation, and this h of u value is basically equal to the behaviors vector, which is expressed as some likes on some pages and so on, times c plus d, where c and d are just the weights that we are trying to train the logistic regressor to fit. Then we want now to consider the neighbors. So we want to use the social graph. For this, we will use the homophily definition, but now we will provide a more formal definition of homophily, and that is if we sample a random edge E between two users U and V from a social graph, then both users U and V are highly likely to either both have an attribute A or not have it. So this is expressed here by this summation over all the neighboring users. So the gamma here expresses the set of neighbors, and V expresses a single neighbor at a time, and J is the homophily term, which we will see now how this can be interpreted. So the user states that this equation can be interpreted using a pairwise Markov random field, and he doesn't give a proof or a reasoning for that, but it will feel like more natural when we see why this is the case. So a pairwise Markov random field is an undirected graph. So meaningly that it's not like the linked list or like a search tree where you have a parent that points to a child or an element that points to another, but the elements are just connected with edges which have no direction, meaning that each node can send nodes can exchange messages in a bidirectional way. So this is a pairwise Markov random field very roughly, and each node has, as we said, a node potential, and you can imagine that as the probability distribution of a variable associated with this node, and there is the edge potential that relates both variables in each node. Okay, so now to express each node, we have the node potential, as we said, phi of u. This phi of u is actually just a function of the prior probabilities that we calculated. This q of u, as you can remember, is just the value that we obtained from the logistic regressor that we have, so just the prior probability. And now the phi of u and v, so the function that expresses both the connection between two nodes here is expressed with some weights called w. So w, the author sets w to the author sets this potential to w if xu xv equals to 1, and sets it to 1 minus w if xu xv equal to -1. And what's the intuition behind that? Xu xv equal to 1 when we are speaking about binary attributes, because all attributes can be converted to a binary attributes as per the user. So this means that xu and xv are similar. Either both are equal to 1 or either are equal to -1. But if the multiplication is equal to -1, then they are different. So it's either 1 and -1 or -1 and 1. And the author sets w to a value that's more than half. This means that xu and v is more than half, so the edge has a more value or has more weight when they are similar, and this is very intuitive. The author actually does not train these weights w, and he states that it will be a very valuable future work if we can train these weights w. He just sets them to values that are more than half, so that this substitution occurs. And he said that this weights w should, of course, express the homophily. Okay, so now we have the posterior probability, which is the probability that's not only given the behaviors, but also given the edges. for a training user V. So the user V is actually a user who is close to our target user U. So we can just calculate the node potential for him, and we also calculate the edge potentials for his neighbors. And then we use something called the Loopy belief propagation. It's actually a way to traverse the pairwise Markov random field. So imagine that we have this pairwise Markov random field. So you have many ways actually to traverse this random field. I'm sorry, I'm not sure if. Oh, yeah, good. So sorry, it's just my screen is. Hello, I'm audible. Hello.
Yeah, we can hear you. It's all good.
I'm sorry. I thought I got a message that I'm disconnected. So can you tell me what was the last part that I was audible at?
You were audible all the time. It's totally fine, and we also see your screen still.
Yeah, that's great. So I just I'm sorry. So okay, so I was just saying that yeah, the loopy belief propagation is just a way to traverse this Markov random field or this undirected graph. So one way to do that, of course, would be like you can consider one of these nodes as a root, and you just pass messages from the root to the parents and then the childs. Of course, this is an undirected graph, but you can define a parent that is as a node which is nearer to the arbitrarily root that you chose, and children are things that are further to it. But the loopy belief propagation actually is another method of traversing this thing, namely by message passing and defining a message function and initializing it, and then iterating over these messages and calculating their values given other messages, and then you compute the error of a message, like you see the difference between the message value for a given iteration and the previous iteration, and if this is so low, you just stop and then compute the probabilities using the given values of messages. So just to recap, it's just like you have messages, you can look at that as some weights initialized, and these messages are computed given the node potentials and edge potentials and given other messages, and then you update new messages and compare that to the previous values, and if the error is so low, you stop the iteration. So now the posterior probability is directly proportional to the prior probability of the users that. So now we are interested in the posterior probability of the target user. The posterior probability here was for some neighbor, but this one is for the target user, and it's directly proportional to the prior probability, of course, because the behaviors, the estimator of the behavior has some contribution to this function, and plus to the messages that are being passed by the node, the neighboring nodes that passed messages to the target user node. And this proportionality can be expressed in an equation into this form. But it's too much details to like derive that. So in this way, when you update the messages, you consider the homophily, and you consider also the behaviors, and then you have a probability that a target user has the attribute X with some good accuracy. So this is the first part. So the second part is the optimization and how this model performs faster than while. And for this, there are two steps done. So the first thing is eliminating message maintenance. So the loopy belief propagation actually needs to save the values for messages per iterations in order that it's able to compute these messages. So the reason behind that, as per the user, is that if we see this photo, is that we do not consider the node connected to a given node if we are sending a message to it. So let's make that more simple. If we want to send a message from B to D, so basically B first asks for messages from its neighbors. Who are the neighbors of B? They are A, C, and D. But because B wants to send a message to D anyway, so it doesn't make sense to take a message from D and then take that as a component that will constitute the message that I will send to D again, because this will not add any information to D. So this fact that I don't get a message from D makes me forces us to save the values for the messages. So the optimization done by the author is that it just takes the message from D, even though I am sending a message back to D. So this will not affect our message positively, but it will not also affect it negatively, and it will not force us to save the message values. So this like simplifies the equation for the message to this, and this is more efficient and quick. I'm sorry if things need to be more explained in detail, but we just don't have much time to do that. So the second optimization technique is linearization. And basically, so this is a very general concept. If you have a nonlinear system, you can linearize it in many ways. So this linearization makes the system produce approximate output as the output it would produce as a nonlinear system. So this linearization made by the author like gets acceptable result, nearly the same result, and it allows the function to be simplified to a matrix form. So the prior probability function is now has this posterior probability. The posterior probability function has this prior probability component plus some matrix form component, which makes this parallelizable and can be used to be parallelized on a GPU or something. So this is basically faster. So the complexity analysis states clearly. You can see from the O of or the order of the execution that our proposed model is faster because we have T times E, where T is the number of iterations and E is the number of edges. Here in Vial, we have T times E plus M2 plus NT. So even though we don't, if you don't know what are these, you can say easily that the one upwards is less than the one underneath. However, M1 and M2 are like total number of attributes for users and total behaviors of users, and NT is just the number of target users. So in the end, I will just present the results. So the experimental setups for this experiment is that we obtain a data set from Google Plus social network. So the behaviors are user ratings on items like applications, books, and music. This is actually what's thought of as behavior for Google social media network. Google Plus is already discontinued. Yeah, the data set used in training is larger than Vial. Vial was the training set used for Vial was 1.1 million users. However, the author states that still, even though the data set is slightly more than the one used for Vial, it's still not sufficient. They need more data set to perform well. Okay, and the target attribute that we will be having is the cities lived attribute. So we want to infer whether a target user lived in a certain city or not. And for that, we take the top 50 cities. The top 50 cities among users, what we mean by top 50, not the general population of the city, but the cities where users indicate on the social media platform that they lived at. And this is guaranteed to like maximize the accuracy, because the more training samples that you have, the more you can get better accuracy. So but just to generalize, the author states that only 3.25% of the users live in these cities. So we are not just taking a very special case, but it's rather an acceptable case too. So We take a chunk of these data, which is 25% of users who provided information about cities lived among these 50 cities, which are about 7,000 users. And we use the library liblinear to train the logistic regression, which is the prior probability part. Yeah, so we don't do anything special about the prior probability part. We just use a library to do that. And the results that we have is that our AttriInfer model outperforms Vial by far, as you can see, in terms of precision, recall, and F-score. We have also like the random guessing. We have the attribute inference behavioral. This is the prior probability part without considering the social graph. This is the part considering the social graph only. As you can see, the part considering the social graph outperforms Vial. So the modeling of the homophily as a Markov random field really did well, even though we didn't use the behaviors yet. It outperforms Vial, although Vial merges both the behaviors and the social graph. But of course, the best performance goes to the attribute inference technique. This ensample technique is just merging the attribute inference, the prior probability technique, the logistic regressor, and the social graph, but with a different technique other than a Markov random field. They are just merged using a final layer that merges two machine learning models like hello?
Is it me or Mahmoud dropped offline?
I'm not sure.
I think it's.
I think I'm connected.
Yes, but your screen stopped shared.
Yeah, okay. So I was just discussing these results. Yeah. So the thing I was discussing here is the difference between the ensample learning technique and the AttriInfer technique. So so it's just that the ensample learning merges the behavioral and the social graph in a different way other than the Markov random field that we have. So yes. Also including the results is the speed. So as we can see, the attribute inference, the basic before optimizing the Markov random field, it's basically faster than Vial, starting from a number of users that's like 200. So it's the use case would be much more than that. And the advanced or the optimized attribute inference is actually faster for a very low number of users. Vial is just faster for like only 10 users, because Vial doesn't have this prior probability logistic regressor. So sometimes if the number of users is so low, then the Vial will be faster, but this is not general case, and it's not also the use case. So basically you are interested in inferring attributes for many users, unless you have this single user as a very important person that you are interested in his attributes. Also, this graph on the left shows that the message iteration using the optimized Markov random field is converging very quickly, like only after 20 iterations it converges. And the last result that the author obtained is that the precision of the model does not depend at all on the index of the city. So this means he means by the index of the city the number of users who stated that they are living in that city arranged descendingly. So number one means that this city has the biggest number of users stating that they lived at that city, and so on. So he just added this result to say that this behavior can like continue not only for the first 50, but maybe the first 200, 300. To a certain point, of course, if there is very low information provided, the performance is expected to degrade. But yeah, it's just robust for the first 50 at least. So that's it from my side. I'm sorry for the disconnections, and I hope this gives you a good idea about this paper. And I'm open for questions now. And I also would like to state that on LSF, on our system of registration for the exams. Today is the deadline, so if somebody did not register yet, today is the last chance to register.
Yes, and please do it. And if you miss it, yes, don't send me emails, huh? Anyway, so joking aside, let's get started with the questions. So, Lucas?
Can you go back one slide, please?
Yes, sure.
I'm not sure. I think I didn't get why the running time doesn't grow linearly with the number of test users, because well, you gave a asymptotic bound of O of t times the number of edges. And
no, for while it grows linearly. For attribute inference, you are correct, but for while it grows linearly, as you can see here. So
yeah.
So yeah, that's why it grows linearly.
But the first term here, it refers to the AttriInference, right?
The t is the number of iterations. The e are the number of
no,
edges.
No, sorry. I mean the first equation here. So O of t times.
Yeah, this is just the number of iterations. Yeah, correct. This is for attribute inference. Yeah.
Here it seems that the number of edges does make a difference here. So if we have more users, then I would say that the number of edges grows quadratically, and therefore I don't really get why the running time stays constant if the number of users grows.
Yeah, I agree with you. I didn't really get that part so well, and I believe that okay, it will grow, but I think because the test this curve is plotted only for a very small number of users, like 300 users, so that edge term does not I mean that you have also that randomness of running trials. So if you run that for like 100 users, 200 users, it can run at the same time. So these are just reported results, but they do not like express reality. I agree with you that if the number of users grows, yeah, if we have an asymptotic growth, like we have 100,000 users, of course this curve will not like continue with the same manner because yeah, the number of edges clearly appear in the equation.
So they probably should have mentioned that, but I also haven't seen it in the paper. Anything?
Yeah, it's not mentioned in the paper of all, because you know when you are introducing a paper, you also want to say you want to show sometimes it should be professional to do that, but you should sometimes show that you are doing well too. Yeah.
Okay, so next one, Julian.
I was wondering if I would train a model yesterday on Facebook, and today there are 1,000 new users. Is there a good way to apply the model on these new users, or do I really have to add them to the graph and train the whole model again?
Well, this is not covered by the scope of this paper. However, I believe that the part where the messages are preserved can be used again. So if you preserve the messages between two nodes, like you save the edge potential for some between two nodes, you can like not calculate that again. I mean, you cannot not perform the message passing over all the nodes, but you can do that for only the newly added edges. However, these newly added edges, as you can see in the equation, each message is affected by all the messages that are surrounded by them, and these new users will also like contribute to the old users' messages. So you will always have to calculate all the messages anyway to get the best accuracy. If you try like to take a snapshot of the old messages and just use the old users as a separate graph, then you are like computing that for two different social networks.
Okay.
All right. So next one, Franziska.
Yeah. So you mentioned that this method relies on having really large data sets, and I was wondering, so is it just does it just perform way worse on small scale systems, or is it just completely unviable?
What I was mentioning is not the method being reliant on having a large data set, but it's that the use case for this problem is that it's using a large data set, because when you are an advertising company, if I know like data about Francesca only, that doesn't help that much. I want to know data about all the university students of Zarian University. So it's not about that the method does not work for small data sets, but it's like the use case always needs large will always have large data sets. That's what I mean.
Okay.
Did I get your question correctly? Or?
Yeah, that's thank you.
All right, so Philip.
Yeah, I was just wondering about something similar like Julian. I was wondering what happens if a user is deleted. So if a node stops existing in the graph.
You mean existing in the graph with no connections, or
yeah. So the user deletes its profile, for example, and then the node is missing because if you
yeah, that's pretty logical. That can happen. And I think, yeah, you will have also to recompute the messages, because as you can see, each message is dependent on the messages on the other neighboring message, and each neighboring message is dependent on other messages and so on. So yeah, any change in the graph would require you to recompute. However, you can just take one snapshot at one time and you can obtain the information that you need. I mean, the use case still holds, and you don't have to iteratively make these calculations to have valuable information.
Okay, thank you.
Okay, so next one, Benjamin.
Hi, so I think this time I was able to unmute myself correctly.
Yes.
So in the first iteration of the AttriInfer, there were two major drawbacks. The first one was that it was not scalable, and the second one was that it doesn't always converge. And you explained two methods how they fixed that, and I think they are quite technical. Could you maybe give a very high-level explanation how they did it, so that maybe I can understand it as well?
Okay, so we have linearization is just a concept for any nonlinear computation. Mainly, nonlinear computations are always heavier than linear computations, and linearization is a technique that we even use when we are computing things by hand in exams or something. So it's quite expected that if you like linearize a nonlinear system, the computation will be simplified. And here, this is the case that these computations couldn't be expressed as a matrix form before performing linearization, but afterwards you could express that at a matrix form, and hence you can make parallel computations on GPUs. So is that clear enough for this part?
Yes, I understood that.
Okay, and for the eliminating message maintenance, this is something that the author did not mention, but what he mentioned is that if you are computing the message passed from B to D, okay, then what happens in the loopy belief propagation, which is the technique that we use to traverse this graph, is that B asks for messages from its neighbors, which will be in this case A, C, and D, okay? But since I am trying to produce a message to be sent from B to D, it makes no sense to get a message from D and use this as a component to constitute the message that will be sent to D again, okay? So so eliminating this in the equation, so like disregarding this message in the equation forces us to keep these messages saved somewhere in order not to he didn't specify that. I mean, he didn't mention why you do have to save these messages in order to eliminate this message, but he says that it's the case, and he says that by including this message, you can just don't save that, and hence you have more memory. So if you have more memory, when you don't have to save things, then you can just have a faster computation. Okay.
Okay. Thank you very much.
All right. So, Leonard.
My question is some kind of related to the prior one, because I was wondering how in the complexity part you mentioned, why the number of users in the dataset is completely irrelevant in the Markov random field. So actually, exactly on this slide, I'm like, I got that D is computed by only querying A and C, but C. So A and C also must have been computed somehow. Am I right? So it is still some kind of a random walk. What am I missing there?
Well, the thing is, the node potentials and the edge potentials are not are like computed using. I mean they are computed using prior messages. So you can think of that as that they are function of the edges more of the users, and that's because for a social network actually. An extra user would be useless if he doesn't if he does not rely on an edge. So yes, the answer to your question shortly is yes. We depend on the number of users, but in the sense of this equation, on the complexity equation, the number of users here is included not because we have the number of users in the computation of the prior probability. This is already expressed in the edge term. The number of users here is included because Vial computes this attribute prediction per user. I mean, you have to make this. You have to make whatever done by Vial. Of course, I didn't read the paper of Vial, but you have to do whatever done by Vial n times if you are gonna predict this for n users. But in our case, we have to do this only once. And of course, the number of users scales, but this is already well represented in the number of edges here.
Yes. Okay. Thanks. I got it now.
Okay.
All right. So, Lisa?
Hello. I just overflew your paper. So yes, I overflew your paper. And there was under the threat model attack procedure. There was told that in order to use this method to perform this attribute inference attack, the attacker first needs to collect public social graph user behavior. So that means the attacker effectively needs to do the same work the data was collected for, so he can interfere with this. So he needs...
you mean that you mean that the attacker is trying to predict something using something that he already needs to collect, right?
Yeah.
And this can be problematic. Well, yeah, this is life. You mean like no. I will just explain more. I mean that some users like to share information about them, like for example, to express that they are successful about something, to express their marriage and so on. And some people have like private concern to share such things about their work or their career or so on. So you will always have this public information shared on some social media platform. That's why a social media platform exists, because people share information about each other. So you will have this information, and just your task is to use the available information to infer the incomplete information. So yeah, it's not like I'm trying to predict the same thing I'm asked to collect. No, I'm collecting something that's already available, and it's guaranteed to be available because this is a social network, and I use it to just like violate the privacy of people in order to say that in a clear way.
Okay, then I misunderstood this path. Thank you for clarification.
Right, I think that's it for this week. So thanks a lot, guys.